Good morning, good afternoon, or good evening. We're going to work on lesson 2.3 and 2.4 today for stats. So finishing up our little lesson chapter on graphing. And you should be on page 67. So we're talking about some additional displays of quantitative data. The first one we're going to look at is a stem and leaf plot here. So a stem and leaf plot is a graphical display of quantitative data along with their frequencies. The rightmost digit forms the leaf. So you can see down here, these are the leaves. The 7, 8 right here, those are individual leaves. The 7 is a leaf and the 8 is a leaf. All digits to the left of the rightmost digit form the stem. So all of these digits are the stems. A lot of times it'll just be 1, 2, 3, 4. This one they broke into halves. So this is the first half of the ones. This is the second half of the ones. This is the first half of the twos. This is the second half of the twos. Numbers are often rounded to fit into the stem and leaf structure. And so this one would be considered one of those split stems, a technique used to keep stem and leaf plots from being too crowded. For example, if there are 2 stems, then leaves 0 through 4 belong to the first stem and leaves 5 through 9 belong to the second. So that's what this is. It's a split stem. So example 1 here says the following data shows the prevalence rates, numbers with disease per 100,000 residents of chlamydia in 2018 for all 50 states, including DC and the 4 US territories. The data set includes all states, DC, Puerto Rico, and the Virgin Islands. This means there are a total of how many leaves? So there are 55 leaves. Michigan appears in the chart as 5:1. Interpret this value for Michigan. So 5:1, let's go to our chart here. It says the decimal point is 2 digits to the right of the colon. So if the colon is here and we have 1, that means we would go 1 and another decimal place. So 0, 1, 0. So this would be 110 per 100,000 residents. So for Michigan, this would be 510 cases of chlamydia per 100,000 residents. How many states have rates above Michigan? What percentage of the states are above Michigan? Okay. So above Michigan would be above 510, 5 and 1. So either we count that there's 2 other states that also have 1s, or we don't count them. So if we don't count them, then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So 27 out of the 55. And 27 out of 55 brings us to 49.1%. So 27 of them have rates above Michigan. That's 49.1%. Compare and contrast this stem and leaf plot with a histogram. So compare and contrast. So comparing means we're going to talk about something similar. So something similar to a histogram is you can see where the highest frequencies are. You can visually see where highest frequencies are. Contrast means what is different. So something that's different here in a histogram, you don't see the raw data, but in a stem and leaf chart, you see the raw data. So that can be a benefit to be able to see the raw data. Okay, stem-and-leaf plot. So back to our frequency distributions. We've done those, we've looked at these before earlier in chapter 2, but we're going to look at a polygon, class midpoints and frequency polygons. So a class midpoint is the number in the middle of the class. Class midpoint means it's the mean or the average of the consecutive lower class limits. Okay. If a distribution has consistent class width, you can use it to find the midpoints. Warning, often distributions have inconsistent width. For example, we will see examples where they have an inconsistent width, and there actually might be one in the chapter 2 review worksheet, so we'll look at that later. For open-ended classes, classes lacking neither a lower or upper limit, use the class width to determine the class midpoint as if the distribution was not open-ended. So this means it's not open-ended, but it's open-ended below and it's open-ended above. So we're going to use the consistency to help us build that. So it says a frequency polygon, a line graph that uses class midpoints on the horizontal axis and frequency or number on the vertical axis. Relative frequency polygons use relative frequency or percent on the vertical axis. There should be fake starting and ending classes with frequency 0. Okay, so fake classes. So you can see here that let's find our class midpoint. So go back to the definition. Class midpoint is the mean of consecutive lower class limits. Well, we can't use the first one because it doesn't have a boundary. So we're going to have to start with the next 2. So we're going to take the average of these 2 lower class limits. So that's going to go here in this one. So it's going to be 40 plus 50 divided by 2 is 90 divided by 2 is 45. And then likewise, we would do the next. So 50 plus 60 divided by 2 is 110 divided by 2 is 55. So let's see if that's our pattern. We see that these are 10 apart, these 2 midpoints. And then we can go over here and we can also see that these classes, the lower boundaries are 10 apart. So it appears that our width is 10. And you can see that our uppers are also 10 apart. So I think it's safe to say that we can go with that. So that means we can go ahead and just add 10 to find this one at 65, 75, 85. And then we can go ahead and add 10 to make this 95, even though this is not bounded up on top. And that means we can work backwards, 45 minus 10, to make this one bounded at 35 for its midpoint. Okay, so the first midpoint would be 35. But if we go look at the graph, we can see that 35 is right here. So this is a fake class with 0. And this is also a fake class. Just like it described up here, there should be fake starting and ending classes with frequency 0. This is a frequency polygon. Okay. So it says a frequency polygon is drawn below. Circle the fake classes. What is the shape of the distribution? So there's our fake classes like we discussed, and the shape of our distribution is definitely skewed left. Because it's always skewed where it's thinnest. Okay. That's our frequency polygon. Next up, so page 69, here we are. Cumulative frequencies, the sum of all previous frequencies up to and including the current class. Cumulative relative frequency is like a cumulative percent. The sum of all previous relative frequencies or percents up to and including the current class. These can be written as fractions, decimals, or percentages. These values are important for the concept of percentile, but that's later in 3.4. So they are asking us to continue with our Math 133 exam data. And this is going to be our current data here that we're using. So we have below 39.9, we have 5 students, the relative frequency, cumulative frequency, and cumulative relative. So the cumulative frequency is all based on just this number. So this kind of dictates that. So let's start with that. So we have our first class has 5. And cumulative means we're adding, we're accumulating. So the next one is going to be this 5 plus this 5. I'm sorry, this 5 plus this 8, which is 13. Then down below, we're accumulating again. So now we're adding the previous 13 plus the current 16 to get us to 29. And then we're adding 29 to the next individual, which is 25, to get us to 54. And then we have 54 plus the 32 to get us to 86. We have 86 plus 45 to get us to 131. And then we have 131 plus 34 to get us to 165. Okay, and that's what our total number here should add up to, is 165. 5, 8. So 165. Now, our relative frequency is like the decimal form of our percentage here. So it's always going to be the number in that class divided by the total, which is 165. So this is going to be 5 divided by 165, 8 divided by 165, and so on and so forth. So this is 0.030. This is 0.048. And this is 0.097 rounded appropriately. So this one is 0.152. There we go, stand correctly. So 0.194. So 45. 65 is 0.273. And then 34 divided by 165 is 0.206. Now, our relative frequency is what we use for our cumulative relative frequency. So we're going to start with the very first class, the relative frequency from that, which is 0.030. And then you're going to add the next one. So you can say 0.030 plus 0.048. Oops. Which is going to be 0.078. Another way that you can do that would be just to take your cumulative frequency, what those totals come out to be, and divide by 165. So that should also be the same as 13 divided by 165. Should also give us to 0.078. And that would round to 0.079 rounded. So depending on your rounding. So the next one would be 29 divided by 165 would be 0.176 if you round. 327. This is 0.521. And look at, we're getting closer and closer to getting closer to 0.999, which will lead us to 0.1 to 1.0. 131 is 0.794, and then 65 will get us to 1. What percentage of students scores 79.9% or below on the final exam? So right here, 79.9% or below. What percentage? So that would be, go over to this cumulative, right? And that would be up to this 0.521. So 52.1% of students scored 79.9% or below. The next graph that we're going to talk about is an ogive. An ogive is a line graph that uses upper class limits on the horizontal axis and cumulative relative frequency on the vertical axis. So upper class limits on the horizontal and cumulative relative frequency on the vertical. There's a fake first class that has cumulative relative frequency or cumulative relative frequency of 0. These graphs are particularly useful in cumulative percent as growth charts. So if you remember going to the doctor when you're little, or if you have little children yourself, this is like what they use at the doctor's office. So continuing with our Math 133 final exam data, which type of ogive is drawn here? And it's a cumulative relative. What is the first class of the cumulative frequency distribution? So this is the fake class. So this is the first class. But you have to remember that that is the upper class, because remember it uses the upper class limit. So this is the upper class limit, 39.9. And so the lower class limit is just above this, which would be just above this fake class of 29.9, so 30. What is the third class of the cumulative frequency distribution? So there's the first class, the second, there's the third right here. So that would be 50 to 59.9. Interpret the meaning of a dot at x equals 69.9. So this dot right here actually goes over. Oops, there. So that shows us, so a little over 30%, like 33% or so. So approximately 33% of students scored below that 69.9%. Okay. The next one is called the time series plot. A line graph that uses time on the horizontal axis and the measure of some variable on the vertical axis. So you can see in this one, our time is in years. It's the unemployment rates of Black and white Americans between 1990 through 2019. So 1990, this is 2015 right here. So 2016, 2017, 2018, 2019. Estimate the unemployment rate for white Americans in 2010. So white Americans are right here. And it looks like these go by 1%. So 15, 16, 17, 18, 19, 20. So approximately 16%. Oh, I looked at the wrong sheet. That's down here. It's this one right here. So this is where, so about 9%. So just below 9%. We'll see approximately 8.9%. Interpret this value. Approximately 8.9% of white Americans were unemployed in 2010. Estimate the unemployment rate for Black Americans 2010. That was the 16%. Approximately 16% of Americans were unemployed in 2010. Use some important characteristics of this graph. List some important characteristics. What is this? What does the graph reveal about unemployment in the US over this 30-year period? So it was definitely up and down. So there was some volatility. That means it's up and down, some volatility. And white Americans and Black Americans, they kind of went up and down together. The gap is getting closer together, I would say here. So here's the gap between white and Black Americans is getting closer together. That's a good thing. So the next little section is just 2.4. 2.4 is all about graphical misrepresentations of data. And there are plenty of good things to look at here. So good graphs avoid the following. They do not have graphs that have these examples here. Unlabeled axes, no labels here. Truncated vertical axis. So this vertical axis does not start at 0. That's really bad. discontinuity in vertical or horizontal axis. So here, this goes 0 to 50. So by 50, by 50, by 50. But this starts at 2005. So it's not really coming together there. Choose an inappropriate vertical or horizontal axis scale. Yeah. So average home price. So kind of hard to follow here. Labeling is not good. Poor use of double y-axes. Oh yeah, this is really bad here. Better use of double y-axis, same data set. So same data set, at least they had some vertical axis here, a little bit better description. So these are not good. Guidelines for constructing good graphs. A good graph has a title and label the graph's axes clearly, providing explanations if you need to. You need to have units of measurement. That's important. Avoid distortion. Never lie about or exaggerate the data. Minimize the amount of white space in the graph. Avoid clutter. Avoid three-dimensional. That's usually a really bad graph. Do not use more than one design in the same graphic. And avoid relative graphs that are devoid of data or scales. So this scaling is very hard to follow. Not good. You can't even tell what applies to what. You don't even know what it's about. There's no label on this one. The labeling here over on your axes, we don't even know what these represent. So horrible labeling on this one, on both of those. Example 2 here says, what is wrong with the following graphs? No, these came from a journalism professor's website. Interesting. Among mothers of school-age children, most admit to eating fast food at least once in a week. This is like some weird 3D. It looks like a sandwich they're trying to break it into. So it doesn't even really make a circle shape. So that's kind of weird. Weekly US retail gasoline prices. Regular grade. So it doesn't start at 0. That's definitely a bad thing there for the gas price. So we definitely want to compare it to 0. That one's not good. Oh, and then the candy bars has got its whole thing going on. There's no measurements. There's no axes here. It just basically shows us that a Hershey's is longer. So that sums that right up. So that is the ending of our chapter on graphing, and we'll catch you back for chapter 3.1.